Alright, here I want to record some quick notes on Houdini channel operators, specifically concerning audio signal processing. First, there are quite a few loads that are interesting to the audio specifically. Here we have the audio, the file load, the wave, noise, which I will demonstrate, and the filter load. Envelope is also interesting. Spectrum is something I will talk about specifically. Some of the other stuff that ChatGPT mentions do not really exist, so ignore that. That's the first part. The second part is, let's take a look at the wave load first. So before you can hear anything, the thing to set up is go to the audio panel, select scrub, and select the output from your channel. Here I'm using this output. And with that setup, what you can do is you can just drag anything inside here, and if you just play from the start, make sure you have real-time toggled, you will be able to hear it, right? So here for the wave, I'm setting up some basic frequencies, and here I am using this one. So the C4 chord frequencies 261, 329, 392, that's in hertz. If you convert hertz to the corresponding seconds, so you can find these values, and I'm essentially just pasting those values inside here for those keys, C4, E4, and G4. So that's a C4 major. And what we have here is, if we listen to some of it, that's E4, right? And this is G4. Right. So if you combine all of them together, here I'm using a mask node to combine all the three together. Here the thing you need to do is to make sure combine chops is add. The combined channels apparently do not work in this case. I think they are combining the channels of each stream. In this case we have 3 streams and each one has 1 channel. So really we need to use the combined chops. In that case we have the final result here. And if we hear that one, right, so that's the result. Just in case you don't really believe that, here inside Divuka, I'm having the same example here. If I do a sine wave, and then this is right, so this is a C4, and this is a E4, and this is a G4. Right, so if you combine everything together, and it actually sounds quite similar to the one we get here. Okay, so that is how you can synthesize primitive sinusoidal waves. In terms of spectral node is actually very interesting. It took me a while to figure it out. So if we just grab one of the waves, this is C4, and if we just drop in the spectral node and put this inside, and if you just take a look at this one, I'm going to hide the other one, you will see that it is supposed to give you frequency domain outputs. And the one important option here is the analyze segment. If you are trying to analyze the entire segment, you should typically turn this off. So for this one, I am generating a single channel at 48K samples per second with about 10 seconds of audio, right? Because this is a single frequency, we expect to see a single spike. When you pass that audio channel through the spectrum, it is going to generate, depending on whether you specified phase, it will generate either a single channel representing the magnitude or 2 channels representing both a magnitude and the phase. So here if I do P, that will give me 2 channels, and the channel name is going to be named after the input channel plus the suffix. The suffix is the suffix we specified above, right? So I'm not going to show the phase, to just visualize the magnitude, and this is something took me a while to figure out. You can see that there is a message here: multiply the index by some value to get the frequency at any sample. What that means is if you drop in a stretch load, and I'm going to explain that, and set the value to the value that it is suggesting, 0.09, and visualize this one, and if you can connect this one to vertically adapt the whole range, you can see now we have a value here. If you take a look at the lower left corner, that's about the frequency we're targeting. So 256, which is, I'm not positioning precisely, but you get the idea, right? So what this one really does, if you take a look at the spectrum output, it actually generates the same number of samples for the entire 10-second frames. But the horizontal axis, the time axis of those samples are actually representing the frequency, and the value of those samples are representing, I suppose in this case, some kind of coefficient after the fast Fourier transform. And what this message is telling you that in order to get the actual frequency, you need to multiply this value to essentially stretch this whole samples into a smaller range. And that's what we are doing here by compressing the entire range. Let me just draw an illustration. So what we are doing here is we are compressing a much larger range with the 10 seconds worth of samples in quotes into a much smaller range that is actually in frequency domain, right? So that's what we are doing here. And here you can see there should be a single spike. If on the other hand we take a look at the frequency output of this, you can see that we have, oh, where's the other one? Oh, I accidentally deleted one of it. So if we do this one, and if we draw this one, you see we have 3 spikes because we have 3 sinusoidal inputs, right? So that is how the spectrum load works. To prove it actually works, what we can do is, here I have a file. That's my recording of some audio. Actually, well, I'm not going to use this one because it doesn't sound very good. I'm going to drop another file, and here I'm going to pick a music. So the music is from Envato Elements, and I put that as the output. If you listen to that, right? So that's some music. I'm going to use the spectrum to analyze it, and I'm going to analyze the entire duration. So that will output the frequency domain information. Now, the spectrum load works in a pair. If you drop in another spectrum load, plug this in, and in this case, you change it to from this frequency spectrum. What is going to happen is you can recover. So this is decompose, and this is my music, right? So we are decompose the music into both the magnitude and phase in the frequency domain, and here make sure the suffix matches. The output will be the original audio. Oh, maybe it crashes. Yeah, it crashes. Oh, it doesn't crash. Good. So after the decompose and the compose, we are reconstructing the original output. So if you listen to it again, right, so it sounds the same. This is actually documented. So if you go to a Houdini spectrum load, it does mention something like that. So here it mentions the use of magnitude and phase suffix, and in order to convert back to a signal, both channels are required, and the suffix should be the same, right? So that is indeed mentioned. So that is this part on the spectrum load, and here we talk about basic synthesize. And here let's take a look at something else I was trying to do, but turns out it's trickier than I expected. So here I have a recording. The recording is just me saying something. And where's my output? The output. Actually, before I talk about that, there's another thing you can do in order to do audio processing. So here I have this guy. You can very easily do basic audio processing with Chop by, for instance, we can drop in a mass node, put that in, and we can do a, just make the volume smaller. Oh, where's my law node? So I forgot that. So this is my law, my output, and make sure I still have it here. Scroll up, find the thing, the output. Okay, good. So that is the audio now at a smaller volume, right? At a smaller volume. So you can easily output your processed result by using a drop channel output, and you can specify the output path as a WAV file, and then no need to pick the entire range, just render a current frame and save to disk. That will actually save the entire audio range, the entire channel, in fact. So also the channel name doesn't really matter. We have channel 0 and 1. It's going to be a stereo audio. So the output is this guy. Actually, you can see from the file size, it's exactly the same as the original one, right? So that is how you can output something from the chop context in terms of audio signal. Now, if we talk about one last example I was trying to do, which turns out to be trickier than I expected. So here we have some recording, and that is me saying something. Hello world. Hello, boo boo boo. Okay, so this what I'm trying to show is I have actually two ranges of kind of speech. If we draw this guy, what you should be able to see is we have kind of two different peaks. The first one is there's like a peak somewhere here in the lower range of my voice, and somewhere here I suppose represents the last bit of my vocal. One interesting reference is here, and that's something I wanted to show. So the human vocal range is from 85 to 155, which is, I find it a little bit weird, and this is the part I don't fully understand. Okay, this is the part I don't fully understand. I find it a little bit weird, not exactly match my expectation. Looks like the majority of output is at this range, right? And if we go to this one, you can see, by the way, this output has some issue. It's a 75 to 300 hertz and 100 to 400 hertz. At the higher range, it's 135 to 500, 180 to 700, and 250 to 1100. So that is the frequency range of humans. Now, in terms of the audio files, the sample rate we have is 48K, right? That is the sample rate, but the actual frequency range of the sound that the file can reproduce is half of that. So for 48K, what you get is 24K, right? So that would represent the human hearing range from 20 hertz to 20 kilohertz. So that is some basic numbers to keep in mind. And with this one other thing I want to mention is, so if you are using Audacity, and here I'm inputting some the combined chord. If you listen to it, so that's the combined chord. You can do an analysis, select everything, and analyze, go to plot spectrum, and you can plot spectrum, right? By default, it's going to use the Hamming window, which I find a bit weird. I'm not expert in this, but I find this a little bit weird. So I find the rectangle window makes a bit more sense to me. And the way you read this one, this 0 dB represent the maximum audio that your speaker can produce. Okay, like you can see like a 1. And this lower range represent how far it's deviating from 1. Basically, if it's very low, like as here, it means the audio level is 0. Anything between, it's closer to how much your speaker can produce. So the way you read it is like you see somewhere in this range, we are producing those high peaks at the almost the maximum level that our speaker can produce. So that's the way you read this one. The dimension kind of reads like in this direction. It's a little bit different from the spectrum output from the Houdini. So that's something I want to mention. The other thing I want to mention is for the same recording, like this one, hello world, right? So for the same recording we have, the spectrum analysis result here is showing me, I think, a bit more information than what Houdini is showing. So if we make it more refined, actually I'm not sure what this size does, but looks like the bigger the size, more refined. Actually I have no idea what this one does, but it looks like we have quite a few peaks here, and this is a more accurate depiction. So from the range of 80, so from here from the range of 80 to the range of the 340, and we have another peak here at about 11k, 1100, compared to the one we have here, which, you know, we don't see anything at the higher. I mean, we do see a little bit. By the way, this is like linear scale, right? This is a logarithmic scale, so the scale is going to be different. But you know, just want to point out, you know, maybe there are some similarity between the two, maybe not. So just want to point this out. Okay, so that is the thing regarding spectral analysis in Audacity. One other thing I want to mention is here, what I'm doing here is I have this original recording, right? And I have another one representing noise. Okay, it may not sound very obvious, so that's why I have a mask to multiply it by 10 times. So it, you know, it is louder. Right, so that is some background noise. If you take a look at the spectrum of this background noise, actually doesn't look like this. Put it here. If you take a look at the noise profile, you can see that it's very hard to see anything because the level is very low. So if you right a middle click, you can see the maximum value is only 0.0027. After spectral analysis, the maximum value is 0.006. So you can barely see anything here. What you can do is I'm going to add another mask and plug this in, make it like much bigger, and then we can visualize this guy, and then you can start to see something, right? So the noise profile looks like, and that's something I was trying to do, but I didn't actually succeed. I suppose it's more complicated than that. The noise profile looks like it's centered around the lower range. So what I was trying to do is I'm intentionally adding noise to my audio by, of course, you know, making the noise much bigger and then adding it to the original sound. So like this, right? So the original sound is like that, and I'm adding noise on top of it. So here, if you listen to it, hello world, you can hear both myself and also the background noise. And here, what I'm trying to do is to use a low, to use a band stop, a band pass filter. So a low pass means anything below this frequency, we're pass. Anything high pass means anything above this one we're pass. Actually, I think the documentation explains a little bit clearer. So if you go to the band filter, you can see that what it's trying to do. Not band filter. Yeah, band filter. Wait, not this one. So pass filter. Sorry. So pass filter. What you can see here is that low pass filter, all frequencies below the high cutoff are passed, right? And the high pass filter, anything above it, and the band pass filter is anything between. The band stop filter is like an invert of the band pass filter. So I was thinking, maybe if I use a band stop, and if I can pinpoint the exact frequencies that represent the noise, I would be able to do kind of like a denoise, right? Apparently it doesn't really work. Sometimes, I don't know, sometimes you need to reconnect it in order to hear anything. Or sometimes it just doesn't give you anything at all. Yeah, this is one thing I don't know. Hello world, right? So I can hear something, but here it should still give me something, but it is not. When I was testing, sometimes it works, sometimes it doesn't work. I don't know what exactly is going on here. Like even if you increase the value, it still doesn't produce anything. Yeah, sometimes it works, sometimes it doesn't. I am not sure why. What does this one do? This is the output. What about I do this? Yeah, like anyway, the end result is this doesn't work, and the reason it doesn't work is if you look at the original recording, and if you look very closely to the lower range here, you will see that, you know, it looks like there's nothing going on in this region, but really there is a lot going on in this region, and we can kind of see it by adding another mask and give it some range here and visualize this guy. And oh wait, what was I doing here? No, not like this. Okay, so what am I going to do? I'm going to do another band pass filter, and I'm going to do a band pass from 40 to 80, right? And oh, actually, damn, this doesn't work. Okay, I don't quite remember how did I set up. Okay, let me just tell you. There is something going on there. There's a lot of stuff going on here. So if I was trying to just remove the noise, because what I observe is the noise tend to center around, this region, and if I just try to remove this region, it will not work, because apparently the original thing do have a lot going on. Actually, you can kind of see here, right? We do have a lot going on in the original recording, so you cannot just remove noise like this. Although I don't know why this one doesn't produce anything. It should at least show me a little bit audio. It just sometimes doesn't work. Okay, so that's everything about the chop context and how it can be used for the audio signal processing. Apparently there's a lot yet to be figured out, but I'm just making this recording as a quick reference for some of the discoveries I made so far.